All right, so what we are going to be looking at is what we did in class today, January 9th. I passed this assignment out, and this is the reading the text where you can get information from. We went over that we have a quiz on January 13th and a test on January 20th. The quiz will be over the first half of this text, and the test will be over the whole 6 pages of this information. So we are taking this apart and dissecting this today as a class. And so what we did is we looked over the standards here that the state of Georgia asked that we use, and then we began to read. Some classes we read together, some classes we read in small groups, but we took a highlighter and we highlighted the important information as we read. So we read through all of these bullet points here, and we talked about each one. So let's go through phases and phase changes. So first here it says all matter is composed of small particles, atoms, ions, and molecules, which are in constant motion. So we've talked about atoms before. You've talked about them in 8th grade. And remember, an ion, a molecule are just forms of atoms. An ion is a charged atom. A molecule is bonded atoms together. So this is important here that they're in constant motion. All matter on Earth is generally found in one of 3 different states, a solid, liquid, or a gas. So again, that says all matter on Earth, because there is another common state of matter that's much rarer on Earth, and that's your plasma. So those are your 4 states of matter there. And then here it says the state of matter that a substance has depends on the arrangement of the particles, so that's something, the attraction of the particles, between the particles, and the amount of energy that the particles possess. So think about that. If I have something that's a solid, there is a specific arrangement of those particles. If it's a solid, they look the same way. They're going to be in a certain spot. There's a certain attraction, a certain level of attraction they have between those particles, and there's a certain amount of energy. If I change one of those things, if I change the way the particles are arranged, I can do that by adding energy or taking out energy. And if I do that, it's going to also change the way that those particles are attracted to each other. They're going to have enough energy to where too much energy, they don't really notice that much attraction to each other, and they can spread out. If they have less energy, the attraction forces are pulling them closer together. So if I change one of those 3 things, I'm really changing the other 2, and also that I could possibly have enough change to change the whole state of matter. So I can change it from a solid to a liquid, liquid to gas, or gas to plasma, or back. So the state of matter of a substance is a physical property. And I don't know if you remember what a physical property is, but a physical property is something that describes matter the way that it looks. It doesn't describe the way that it would change. It describes the way that it is. So if something is at room temperature, a solid, you could describe it as a solid. It's just a fact about that object, about what it is. It's either a solid, a liquid, a gas, or a plasma. So the state of matter is just a physical property. The particle arrangement within each state, solid, liquid, gas, plasma, is represented in the diagrams below. Notice that the plasma has 2 kinds of particles, large ions and tiny electrons. So down here you have your particles, and you notice around those solid particles, you notice they're kind of in a boxy shape. The particles are lined up, they're very, very structured, they're very, very close together. And you notice I put little, almost like little parentheses, little bitty things showing that they are vibrating, so they are in motion. A liquid, the same thing, but the liquid is a little more relaxed, and those particles are kind of rolling around and sliding past each other, and they spread out and they fill the bottom of that container. So there's your liquid particles. And then up here you notice that you have your particles, and the arrows are showing the motion again, and they're moving in straight lines all over in random patterns, and gases move very, very quickly. Plasmas, notice that there are large ions and tiny electrons, so there's these little bitty dots here. And what happens is that a plasma, these big particles are your atoms, your ions, okay, because they become charged because they've lost these electrons. But they have so much energy that these particles have lost those electrons. Those electrons have flown off, basically, off of those particles. They've been pulled away from those atoms. So you have free electrons in there. So this one has actually the most energy that there is. Gas has less energy than plasma, but obviously has more energy than a liquid, and so on and so forth. So least amount of energy all the way to the most amount of energy, and then those 2 fall in between. So let's look at the temperature well, actually, let's look at our notes. What we did as a class together is we just formatted some notes. We made our notes, and we put the title, Phases of Matter, and the date. We put our EQ. If you need to, just pause the video and catch up. I'm going to kind of go through this quickly, but pause it where you need to. And then we took the topic, Phases of Matter, which we just read, and then we did the kind of some important things. All matter is made of atoms, okay? 4 phases, solid, liquid, gas, plasma. And then we looked at the state depends on 3 things, and those 3 things came directly from your reading. We underlined them in your reading. They depend on the arrangement of the particles, the attraction between the particles, and the energy of the particles. So that was kind of the information from the first part of the reading, and we discussed in class. So you can pause this and get those, and then we'll move on to the next section. All right, so here we are at thermal energy and particle motion. So right here, we're looking at a relationship between these things. So particles that make up a substance are always in motion. Notice that's the second time you've heard that. Up here at the very first bullet, it talked about it's made up of those atoms that are in constant motion. So the temperature of a substance measures the average energy of the motion or the kinetic energy of the particles in that substance. When the average motion of the particles of a substance decreases, the temperature of that substance decreases. Likewise, an increase in the average motion of the particles increases the temperature of the substance. For example, if a solid room temperature object is placed in a refrigerator, the substance will lose energy and the average motion of its particles will begin to slow down. This will cause the temperature of the object to decrease. Likewise, if a solid room temperature object is placed on a hot plate, the substance will gain energy. The average motion of its particles will begin to speed up, and this will cause the temperature of the object to increase. So once the temperature reaches the freezing, melting, or boiling point, a phase change will occur. And a phase change is a physical change that happens when a substance changes state. So we're going to look at kind of some information here that's important. If I can find my sheet. So one of the things that we're going to look at is the temperature. This is kind of your key term. Put it on one side. Temperature measures the average kinetic energy of the particles. Okay, average kinetic energy. And then kinetic energy itself, remember, is the energy of motion. And pause this if you need to catch up. So remember, kinetic energy is those particles moving around. Remember back when we did energy, we talked about potential and kinetic. Remember, potential is the stored, and kinetic energy is the energy of motion. So we're measuring that motion average as a temperature. And then the motion and temperature have a relationship. So we wrote this down and talked about this. If we have something that is in more motion, it's going to have higher temperature. So when the particles get faster and faster, it's going to show up as a higher temperature. When the particles slow down, less motion, you're going to have lower temperature. All of this comes from what we just read. And then they also talked about the melting point, freezing point, and boiling point. And those are all temperatures where phase changes happens. Those are specific points, and those things are actually physical properties of that matter. So if I say water, water has a specific boiling point. That specific boiling point in Celsius is 100 degrees Celsius. Okay? If it's Fahrenheit, it's 200 degrees Celsius. Water is going to boil. If it's water, it's going to boil at that temperature. If it's not water, if it's some other liquid like vegetable oil or sugar water solution or something else, it's going to have a different boiling point. Same thing here. If we have a melting point and a freezing point, it has a specific temperature. So gold, let's say I find 2 metals that look gold, and I don't know which one's brass and which one's tin and which one's gold. I don't know which one's the pure gold. Gold, if I research it, has a specific melting point. So if I add enough heat, gold will melt at a specific temperature. So if it doesn't melt at that temperature, I know that that thing's not pure gold. So that's just, again, those are physical properties. It's something that you can't change if it's the pure substance of what it is. All right. So now what we're going to do is we're going to look over here at our reading. We're going to read the last little part. talking about during phase changes, the temperature will remain constant, but the thermal energy will increase. That's kind of different. So the temperature will remain constant, but the thermal energy will increase or decrease depending on it. The added thermal energy, if you're adding thermal energy here, it's being used for particles to overcome the attractive forces between them. And that's really important because when we look at this graph, let's take that piece of information and look at this graph here. You notice you've seen this graph before when we studied thermal energy. You have this point of being a solid, and then where it flatlines, it's the same temperature. So if this were water, okay, this temperature right here would be, if we're talking centigrade, Celsius, which this is, it would be 0 degrees Celsius. If it's Fahrenheit, it would be 32 degrees Celsius. So at 32 degrees Fahrenheit, or 0 degrees Celsius, water does a funny thing. It goes from a solid to a liquid. But if it's 32 degrees, I'm going to have, I would have particles of both. I would have solid particles, almost like a slushy, liquid particles and solid particles. I might have areas of where it's starting to crystallize as ice, but I'll still have areas where it is liquid, and vice versa. If I have a solid ice cube and I place it at 32 degrees, I'm going to have areas where that ice cube is going to start to change back into a liquid, condense. So, or not condense, but to melt, So when I'm looking here, that's why at this phase change, the temperature stays the same. So once it's beyond that temperature, higher or lower, that's when it's in the whole other change. But until that time, your temperature is going to be the same because your thermal energy is going to be used to be overcoming those attractive forces between the particles there. All right, so when thermal energy is added, attractive forces lessen, causing particles to move more freely from one another. When thermal energy is taken away, the attractive forces between the particles become greater and cause the particles to stay together. So then you've got your phase changes here, and it's all listed out. And you notice that they're footnoted right here underneath. So if it has 1 star, it means that the energy is being added. If it has 2 stars, it means that energy is being removed. And so in class, one of the things that we wanted to look at is this organizer right here. This is real important because it shows the different phases of matter, solid, liquid, gas, and plasma, and it shows what you call those changes in between. Most of these, freezing and melting, vaporization, condensation, even sublimation and deposition, going directly from a solid to a gas is the sublimation, gas back to a solid is your deposition. Those are all pretty familiar from 8th grade. The one that may be new for you is the plasma. So if you have something that is gas and you superheat a gas, you add a lot of thermal energy to a gas, you can get that gas to what you call ionize into a plasma. So gas to a plasma is called ionization. From a plasma back to a gas, that change is called recombination, sometimes called deionization, but we're going to call it recombination. And what this arrow is meaning here is this really means the energy. That word means energy, the energy of a system. So you think about it, and that can go both ways. If I am going from a solid to a liquid, I'm increasing the energy. So if I'm going up the ladder, I'm increasing the amount of energy. I have to add energy to make a solid change to a liquid. I have to add energy to make a liquid change to a gas. I have to add energy to make a gas change to a plasma. And the reverse is also true. If I'm coming down the ladder here, if I go from a plasma to a gas, I'm going to have to take away energy from that system. A gas to a liquid, I'm going to have to remove energy from that system, and I'm going to have to remove energy from the system if I want to go from a liquid back to a solid. And then of course right here, going from a solid to a gas, you're adding energy because you're going up the ladder, and that's sublimation, or gas back to a solid, I'm going to remove that amount of energy there. So our very last thing that we put in our notes today is about what happens during a phase change. So here's some things that when we just read, the temperature stays the same, but the thermal energy changes. Remember, TE stands for thermal energy, is used to overcome those attractive forces. So that's why, again, on that chart, why that when you're going through a phase change here, that you have those areas where the temperature's staying the same, but there's still some energy. You see the heat is being added. It actually is moving over. So that hole has got more heat energy, or it's got more thermal energy, but the temperature actually stays the same because those bonds or those attractive forces are being broken there, okay, being overcome. All right, and that's today's notes. And what also that we did is this sheet here. So this is what we had for homework. And this chart, it goes through the 4 states of matter, and it talks to you about what's happening in each state of matter. So what we're going to look at is when you look at the solids, and I'll put another link to this tomorrow. So you got solids, and then you're going to find the information here. So you notice that the particles are arranged very close together. They're ordered. They have a regular pattern. Those might be things that you're going to plug in here. They're close together. They're ordered. They have a regular pattern. Look right here. They remain in a fixed position. Strong attractive forces. Even though solid particles are in a fixed position, there's still motion, so they slightly vibrate when you're talking about particle movement. So there's all types of little goody pieces of information you can pull from these bullets, these facts about solids, and put them into your chart. And that's kind of that strategic reading that we're looking at. So what I would suggest is take your highlighter and go through and highlight some things that are used to describe the solids from your reading, and do the same thing for liquid, gas, plasma, and then decide where it goes in the chart based on the topic that's at the top here. These visual representations, what I want you to do there is make your drawings like this. The visual representations of the particles. You want to show me how the particles are arranged there, and then you also want to add arrows or these little bitty lines to show vibration or to show the movement there as your visual representation. So finish your states of matter chart, and tomorrow in class we'll be doing the comprehension check. You do not have to do comprehension check for homework or anything, so I hope this helps. So we'll see you tomorrow in class.